So last time we were talking about generative models, and we started off with some discussion of generative versus discriminative models. And recall that these are basically both different flavors of probabilistic models, but it depends on what we're trying to predict, what we're conditioning on, and really critically what we're normalizing over. So we talked about discriminative models where you're trying to predict the label y conditioned on your data x, generative models where you're trying to just learn a probability distribution over your data x, and conditional generative models where you want to model the data x conditioned on some user input y, or label y. And recall that these differ in that what you're trying to normalize over, because probability distributions introduce this normalizing effect where all things where different kinds of things need to compete for probability mass due to this normalization constraint of probability distributions. And last time we also went through this taxonomy of different categories of generative models, because it turns out this area of generative modeling has been something people have studied for a very long time, come up with a lot of different categories of methods to try to solve variants of these problems. So we went through this family tree of generative models, where where last time we talked about these explicit density models, where the model outputs some quantity some quantity p of x, either the exact predicted p of x in the case of tractable density models, or some approximate version of p of x in the case of these approximate density models. And then in the case of tractable density, we saw autoregressive as a category of model, and we saw variational autoencoders as an example of something that gives you some approximate density. So recall that autoregressive models, what we did is we took our image, or more generally whatever kind of data we're working with, and we break it up into a sequence. And then for the case of image data, we typically treat this as a sequence of pixel values or even subpixel values. And we usually want these to be discrete. So you treat those subpixel values as 8-bit integers that can each take a value 0 to 255. You string this out into a long sequence of integers, and then model this using some discrete autoregressive sequence model, typically an RNN or a transformer. Then we also saw the variational autoencoders, which were another explicit density model, but now they compute not the exact density, but some approximation to the density, in particular a lower bound to the density. To do this, we jointly trained some encoder network, which is going to input the data x and output a distribution over latent codes z, and a decoder network, which is going to input a latent code z and output a predicted piece of data x. And we were able to jointly train these two networks, the encoder and the decoder, to maximize this variational maximize this variational lower bound to our likelihood function. Recall that maximum likelihood, is one of the key insights behind all generative modeling. That often our objective function for training generative models is somehow to maximize the likelihood of the data that we observe that comes from our true data distribution. So today we're going to continue our discussion of generative models and explore this other half of the family tree, these implicit density models. So in implicit density models, we are no longer going to get access to some actual density value p of x, but these models will sort of implicitly model the probability distribution. And even though we can't compute a density value p of x for any piece of data x, we will be able to sample from the underlying distribution that these models learn. So we'll be able to draw samples from the learned distribution, even if we can't output an actual density value. So the first such model that we'll explore are generative adversarial networks, or usually called GANs. And it's useful to contrast GANs with the variational autoencoders and autoregressive models that we've seen so far. So like we just said, autoregressive models are a likelihood-based method. Their training objective is maximum likelihood. So you write down this parameterized function that is your p of x, where x is a piece of data, and then you maximize this over the data that you observe, trying to do maximum likelihood. And variational autoencoders sort of follow this similar idea, where we write down this approximation to p of x and then maximize that approximation to p of x. And now generative adversarial networks will do something a little bit different. They will give up on directly modeling that p of x, as we just said, but even though they don't explicitly model the p of x or let us get out those density values, they will give us some way to sample from the underlying distribution that the model is fitting. So the setup here is that we'll start by having some finite samples of data, xi, which are assumed to be drawn from some true data distribution, p data. And our goal is we want to be able to draw samples from p data. And recall, P data is something like the true distribution of the universe. This is the distribution that the universe uses to give you samples of your data. And this is likely a very complicated distribution. It involves physics, it involves history, it involves socio-political constraints maybe, right? There's a lot of complication that goes into all the stuff happening in the universe that gives rise to the data that you see. And somehow we want to model that fit some approximate model that tries to match that true data distribution as well as possible, and then allow us to draw new samples from our fitted distribution that look like the original data samples that we observed. So the way that we're going to do this is by introducing a latent variable z. This looks kind of like the latent variable z that we saw in variational autoencoders, where it's going to this latent variable z is going to be distributed according to some known prior distribution p of z that we will write down and control ourselves. And usually this is going to be a unit Gaussian or a uniform distribution, but typically a unit Gaussian, something very simple that we know how to sample from, we know the analytical properties of. And now the setup is that we're going to imagine some data generating process that our network is going to model. So here, we're going to imagine that we sample a z according to our known distribution p of z to get a sampled z, pass that sampled z through a generator network, g of z, and then that x is going to be a sample from some generator distribution pg. And as we vary the parameters or the architecture or the training of our generator network, that is going to induce different kinds of distributions that we sample from in this PG distribution. So the whole goal in GAN training is to try to force this PG distribution, which is induced by our generator network. We want that PG distribution to match the true P data distribution as close as possible. And because if they match, then we could sample a z, pass it through our generator, and now we have a sampled piece of data that looks a lot like our P data. So the picture for this is something like the following. We'll imagine sampling z from our pz to get a concrete latent z, pass it through our generator g, and that will give us a generated image. So the generator network basically is trained to convert a sample from a known distribution z into a sample of our data distribution. But now the question is, how can we force these outputs? How can we force the induced generator distribution PG? How can we force this to match the data distribution P data? And the trick in generative adversarial networks is that we're going to introduce another neural network to do that task for us, right? In the previous versions of generative modeling, VAEs and autoregressive models, we tried to write down some objective function that we could minimize that would force our fit distribution to match the data distribution. Here, we're going to relinquish that control and basically ask another neural network to solve that task for us. So in particular, we're going to train another neural network called the discriminator, D. And this discriminator is going to be tasked with inputting an image, sometimes a real image, sometimes a fake image, and it's going to classify whether that image was fake or real. And then the idea is that these two networks are going to fight. We're going to train the generator to try to fool the discriminator, and we're going to train the discriminator as a classification model to try to correctly discriminate or classify between real data and fake data. And the intuition is that as these two networks fight, then ideally the discriminator will get better, it will get really good, the discriminator will get really good at determining features of real data from fake data, and once the discriminator gets really good, then in order to fool the discriminator into thinking that the generated samples are classified as real, the generator data will need to get closer and closer to producing samples that look like true data. So that's the kind of intuition between generative adversarial networks. So the question is, does the generator network get feedback from the discriminator on whether it's classifying correctly? Yes, and that's crucial for this whole process working. And the type of feedback it gets is gradients, right? This whole thing, this composite system of the generator and the discriminator are just neural networks. We know how to compute gradients through those, and those communicate through that generated image. So we're going to backpropagate from the discriminator all the way through the generated image into the generator. So that's how the generator is going to learn from the discriminator. And then more concretely, we need to write down some actual equations, some actual math that we're going to use to concretize this intuition. So in particular, we're going to jointly train the generator G and the discriminator D with this minimax game. This equation looks maybe a little bit daunting, so we'll walk through each of the terms one by one. So here, we're going to color code this and say that the generator is going to be in blue, the discriminator is going to be in red. And the discriminator is going to be a function that inputs a piece of data x and outputs the probability that that data is real. So in particular, d of x equals 0 means that the discriminator has classified that piece of data x as fake. d of x equals 1 means that the discriminator has classified that piece of data as real. Of course, those are the extreme cases. The discriminator in practice will output some probability that gives you a soft version in between those two decisions. Now imagine what happens if we fix the generator G, and just imagine this problem from the perspective of the discriminator. So then, from the perspective of the discriminator, there's two terms here. One, this first term says the discriminator wants d of x equals 1 for real data. Remember, d of x equals 1 means that the discriminator says that it's real, and this expectation basically says we're going to draw data samples x from the true p-data distribution. We're going to pass those through the discriminator and then take a log, because we almost always work in log space when working with probabilities. And remember, log is a monotonic function, so maximizing log of x is the same as maximizing x. So in this case, this is saying that we want to maximize log of d of x for real data, which is equivalent to saying d of x equals 1 for real data. Now on the other side, this is saying that we're going to take an expectation by sampling priors z, sampling latents z according to our known prior p of z. We're going to take those z's, pass them through the generator, which should give us a generated data sample, and then pass that generated data sample through the discriminator. And now the discriminator wants to classify these are fake samples, so the discriminator wants to classify these as fake. So we need to somehow invert that expression on the left. So here, we want d of x equals 0 to be fake. So one way to say that is to maximize log of 1 minus d of g of z. So this term on the right says the discriminator wants d of x equals 0 for fake data, and the term on the left says discriminator wants d of x equals 1 for real data. Okay, so that's what the discriminator is trying to do. The discriminator is trying to correctly just do this classification task between generated samples and real samples from our data set, and try to classify them correctly as real or fake. Now look at this from the perspective of the generator. So imagine fixing the discriminator and looking at this setup only from the perspective of a generator with a fixed discriminator. Now in this case, this first term doesn't depend on the generator at all, because this first term was just about getting the discriminator to correctly classify the real data samples. So the generator only cares about this term on the right. And intuitively, we want the generator to fool the discriminator into thinking that its samples are real. So that means that the generator wants d of x equals 1 for fake data. So the term is the same. We draw a sample z according to p of z, pass it through the generator to get a generated sample, pass it through the discriminator to get the discriminator's predicted probability on that sample. And now recall the generator wants d of x equals 1. So rather than maximizing this, like we did like the discriminator wanted to, instead we're going to try to minimize this from the perspective of the generator. And that gives us this minimax game. So in particular, we can abstract away all this math by writing it as some scalar function v as a function of g and d. And then we say that the discriminator wants to maximize v, the generator wants to minimize v. And they're going to fight against each other in that way. And then to optimize this, we're going to basically run some gradient descent loop, taking alternating steps, trying to minimize and maximize this with respect to the parameters of the generator and discriminator. So loop while true forever, then update d according to take a gradient descent step, derivative of v with respect to d, and then step plus that gradient, because remember, discriminator is trying to maximize this, so we want to do gradient ascent to try to maximize this term. And then after we make an update on the discriminator weights, then we'll make an update on the generator weights by taking derivative of that v with respect to the generator weights g, and now take a gradient descent step on v because the generator wants to minimize that objective. So that's basically our training. That's basically the way that we train generative adversarial networks. We've got this thing v, which is the value of our minimax game, and we're going to take alternating gradient ascent and gradient descent weights on that objective v, in order like alternatingly update the generator and discriminator. And one thing that's really important to realize when we're training generative adversarial networks is that this v is not a loss function. That means there is no, the absolute value of v basically does not tell us anything about how well the generator and discriminator are solving this problem. Or how well, or really the thing we care about is how well is that induced PG distribution matching the data distribution. And just looking at the value of v doesn't really tell us anything about that. right? Because the value of V sort of depends on how good the discriminator is, right? If the discriminator is really bad, then it's really easy for the generator to fool this and get good numbers. Or if the discriminator is really good, then the generator has to be really good. So there can be sort of different settings of D and G that will lead to the exact same value for V. And that means that generative adversarial networks are often really hard to train, and even hard to tell when they are doing a good job at training, right? Normally when you train neural networks, you have a loss, you try to minimize the loss with respect to the parameters of your network, and you want to see that loss go down over the course of training. But you don't have that with generative adversarial networks. You have the generator loss, you have the discriminator loss, you can try to plot them, but in general, they're pretty meaningless. So with generative adversarial networks, they're really hard to train. Just this objective is sort of fundamentally unstable. You're sort of trying to jointly maximize and minimize the same quantity with respect to different parts, different sets of parameters of the network. So that's kind of inherently a difficult optimization problem. And then even worse, you don't have any value to look at to tell whether or not you're making progress towards a good solution. So generative adversarial networks, they're pretty effective, but they're really hard to train and really hard to tune and really hard to make progress on. So that's sort of the main takeaway for generative adversarial networks. You know, there is one little trick that is kind of useful to think about for when training GANs, is that just to kind of imagine the training dynamics of these things. So at the very start of, imagine at the very beginning of training, your generator is randomly initialized, your discriminator is randomly initialized. What's going to happen? Well, at the very start of training, then your generator is producing completely random noise. That completely random noise is going to look very different from real images. So at the very beginning of training, when the generator is terrible, then the discriminator has a very easy problem. So typically within a couple iterations, the discriminator can like really immediately pick up between real images and these totally garbage random fake images that the random generator is giving you. So that means that at the very start of training, the discriminator is quickly gonna learn to classify these real and fake pretty quickly with pretty high probability. So then it's interesting to plot what is D of G of Z. What is this term as a function of D of G of Z, right? Because that's basically the loss function. That's basically the loss function from the perspective of the generator. So then from the perspective of the generator, we kind of at the beginning of training are somewhere all the way over here. So the discriminator is doing a really good job at treating generated samples as fake, classifying them as fake at the beginning of training, which means that from the discriminator's perspective, it's trying to optimize a loss function that looks something like this. And if you'll notice something, this loss function is flat, or very close to flat at the place where the generator is trying to optimize its parameters. So this means that in practice, when you use this naive objective for training GANs, then the generator has a really hard time learning at the beginning of training. Oh, good question. Is how do you assemble the data set? Like, how do we generate a photo of a unicorn if no unicorn exists? So this P data, that's kind of your choice of P data, right? So whatever data set you happen to assemble from your training set, that's you choosing what is the P data that you're trying to model. So in general, if you want to generate a sample of a thing that looks nothing like anything that you've ever seen before, you're out of luck. It's not going to happen. So the only way that you're generally going to draw samples is if you have something in your training data set that looks kind of like that. So these networks do, like all generative models and all neural networks really, do generalize a little bit, right? So then the hope is that, you know, maybe you've never seen a photorealistic image of a unicorn wearing a Santa Claus hat, but you've seen photorealistic images of horses, you've seen photorealistic images of Santa Claus hats, you've seen drawings of unicorns, you've seen drawings of horses, and somehow you've got enough stuff, even if you've never seen the exact composition of attributes that you want to generate, you've seen enough stuff that's close enough to it that the model can generalize and give you something new. And that's always the hope here. What does this look like from the discriminator's perspective? So then, then if I generated this image of a photorealistic unicorn wearing a Santa Claus hat, then maybe all the textures are really perfect, like the lighting is perfect, the shadows are perfect, the leaves are perfect. So there's no real evidence in the data, in that sample itself to say that this is obviously wrong. Maybe if the discriminator was really, really smart, then the discriminator could somehow know that unicorns don't really exist and having a perfectly photorealistic image of them isn't likely to happen. But that's a pretty hard semantic problem to solve. So in practice, discriminators tend not to really be that smart. Yeah, good question. The idea is, why don't we look at two curves? Why don't we look at one curve saying how good the discriminator is? Why don't we look at one curve saying how good the generator is? Feel free to plot them. They tend to look really useless. And there's probably literally hundreds of research papers of people trying to solve this problem and figure out how do we tweak the GAN objective? How do we not use a log? How do we use a Wasserstein something, a something, like put all kinds of crazy stuff into this to make those curves more interpretable? Hundreds of papers written about it, like 5 years of thousands of people's time. I don't think anybody came up with a good solution. So still, even after like hundreds, thousands of papers training GANs, a lot of people still end up using this vanilla formulation, which tends not to give you very interpretable curves, even when you split it up that way. The question is what happens to the discriminator early in training really important? And the answer is no, because this is unlike any other classification problem we've ever seen before, because this is a non-stationary distribution, right? When you train an image classifier on ImageNet or CFAR or something like that, the data set is fixed, and the model is just trying to classify that static data set well. But in the case of GAN training, the data set that it's trying to fit is changing under it during the course of training. Because, even at the beginning of training, maybe it's the generated images look really bad. It's easy to solve the problem, but then the generator gets better. And now the data set that the discriminator is trying to discriminate changes under it during the course of training. So that means that it's a non-stationary problem and, with very complicated learning dynamics. Yeah, good question. Do these get caught in local minima? Are there a way to kick them out of local minima, train for a while, kick them out? I think, again, hundreds of papers, thousands of papers, lots of heuristics, nothing really stuck. Correct. So you have to train this end to end. So gradients from the discriminator always propagate into the generator. So in particular through this term on the right. So the only way that you're ever getting gradients onto the generator's parameters is actually through the discriminator, right? Unless you have some regularizer in here, but there's no auxiliary term that's telling the generator what to do other than the gradients it gets through the discriminator. And that's again leading to part of the unstable learning problem. Correct. So that P data distribution, that's going to stay fixed over the course of training. All right. So we said, there's this problem that the generator gets low gradients at the course of training. There's a little hack here where rather than trying to maximize log of 1 minus d of g of z, you can instead minimize minus log of d of g of z instead. You can convince yourself offline that those are roughly equivalent, but the TLDR is then it gives you a better curve for the generator to get better gradients at the start of training. So that's really important, and whenever you're training GANs from scratch using this sort of log objective, then this trick to use the modified loss for the generator is really important in practice. So that means that there actually is a 1V that you're computing for the generator, a different V that you're computing for the discriminator, and they aren't quite the same. Okay, there's another question of why might this be a good objective? And I used to have slides that walked through this proof step by step, but I don't think we have time for that today, so I'll just give you the TLDR, and we can refer you to something offline to check. But the TLDR is that this objective is good because you can write down this optimal discriminator, right? So, this is a nested optimization problem where there's an inner maximization over D and outer minimization over G. So if you do a little bit of math, you can actually solve this, this inner maximization problem and write down what is the optimal discriminator. This should actually be this is the optimal discriminator with respect to a particular generator G. And you can just write this down. Of course, even though you can write it down, you can never compute it because it depends on P data. And you can never compute P data because if you had access to the P data density, you'd be done. So you can write this down as an equation on a slide or on a piece of paper, but you can never compute it. And then, once you have this inner objective, once you have sort of maximized this inner objective by writing down the optimal discriminator, then you can show that the outer objective is minimized if and only if PG of X is equal to P data. So at least theoretically, the optimum state of both the discriminator and the generator actually occurs uniquely when PG is equal to P data. So that kind of makes us feel good, but there's a lot of caveats to that theoretical result. The one is that they both assume infinite potential capacity for G and D, that those both assume that your generator and discriminator can in principle represent any function, which of course they can't because they are neural networks of a fixed size and capacity. This also tells us absolutely nothing about whether or not we will converge to this solution. So even though there is this optimum point in this objective landscape, this tells us absolutely nothing about whether we can ever reach there via this gradient descent, gradient ascent, especially with a finite number of data samples. So there's this sort of comforting theoretical result that there is some theoretical justification to GANs, but in practice, this doesn't really hold or give us very strong guarantees. So these GANs, in practice, your generator G and your discriminator D both are going to be parameterized as neural networks. And they used to be CNNs. The GANs kind of fell out of favor before VITs became popular, but I'm sure they would work with VITs as well. And the first GAN that really gave non-trivial results was called DC-GAN, that had this 5-layer COMNET architecture, which gave these what were at the time pretty exciting samples. And I mentioned DC-GAN because the first author, Alec Radford et al., for most people, doing DC-GAN would have been the highlight of their career. But for Alec Radford, it wasn't nearly enough for him, because the next project he worked on right after DC-GAN, does anybody know? GPT. So Alec Radford, DC-GAN was kind of a low light in his career. He went on to do GPT-1 and GPT-2, as well as some other amazing work at OpenAI. So I think there's this really cool connection between, people that were working on generative modeling of images actually jumped over to do generative modeling of discrete text data and did some of the really important work there. And one of the only other GAN paper that I'm going to highlight is called StyleGAN. I'm not really going to walk you through the details of this one other than to kind of point you at it as like a good one to read if you want to know kind of the best practices of GANs. They use a much more complicated architecture, but they get pretty good results in practice. And one really nice thing about GANs is that they actually tend to learn something smooth in the latent space. So what I mean that is that if we have two latent vectors Z0 and Z1 and we interpolate between them, that is, you draw a sample Z0 from your Gaussian, you draw a sample Z1 from your Gaussian, then you interpolate some kind of curve between Z0 and Z1. Then for every point along the curve, we're going to generate a sample using our generator. Then if we do that, we tend to get smooth interpolations to this latent space, which is something really cool with GANs. And here's an example of this latent space interpolation from the StyleGAN 3 paper. So you can see that these are all generated samples by smoothly varying that latent Z and then passing it through the generator to generate these different samples. And you can see that these animals sort of smoothly morph into each other. So that means that the model has somehow uncovered some useful structure and stuffed it into the latent space. So that's pretty cool. So I used to talk a lot more about generative adversarial networks. The pros is basically they have a really fairly simple formulation. And if you tune them right, like we saw with StyleGAN 3, then they can actually give you very nice results. Very beautiful images, very high resolution, very good stuff. But the cons, like we talked about, they're fairly unstable to train. You have no loss curve to look at. You have very unstable training. They tend to blow up at the drop of a hat. So you end up with what's called mode collapse. All of a sudden you might get nans, you might get infs, your generator, your discriminator starts going crazy, your generator starts producing complete random garbage all the time. You have no loss curves to look at to diagnose this. They're kind of a mess. So even though that GANs can give you really nice results if you very, very carefully tune them, and very, very carefully control the normalization, the sampling, everything about them, they have been, in practice, they've been fairly hard to scale up to really big models, to really big data. So GANs were basically the go-to category of generative models from around 2016 to maybe around 2020, 2021, something around there. And in that 5 years, there were literally thousands and thousands of papers, people both trying to use different GAN formulations, different loss functions, different mathematical formalisms, as well as applying GANs to all kinds of different generative modeling tasks that you can imagine. So this was basically the go-to generative modeling framework for about 5 or 6 years. Question is, would we just expect this? Shouldn't we just expect these smooth latents to pop out? I think not necessarily, because one thing that can happen with GANs is the generator might just memorize a fixed number of data samples, right? So what if your generator ignores the latent Z and just memorizes 10 samples from the training data set somehow? And then no matter what Z you give it, it always gives you one of those 10 samples from the training data set, and it never gives you anything else. Then in that case, you're going to fool the discriminator because the generator is always giving you something which is maybe bitwise identical to one of your real samples. And then in that case, the generator would have basically piled on sort of Dirac delta density, in the immediate vicinity of a couple finite samples, but put no probability mass anywhere else. So that actually is kind of a legitimate solution for the generator. And that would definitely not give you smooth latents at all. So that's just one example of how these things can collapse into unintuitive solutions that are not what you want. Oh, good question. What is the relationship between your training data set and your latents? So this is actually something very fundamental about GANs. It's a great question. So you can map one way. So the generator gives you a mapping from latent space into data space, maps from Z to an X. But with GANs, you in general have no way to map back from an X to a Z. And that's something very different between GANs and VAEs. So VAEs will learn an explicit mapping from X back to Z, but with GANs you have no such thing. You can try to compute an inverse analytically, numerically via gradient descent. And there's papers that do that. But there's actually like no explicitly enforced relationship between X and Z. Instead, you can think of the discriminator as trying to just enforce a distributional alignment between the distribution of all the outputs coming from the generator and the distribution of all the data samples without any kind of explicit supervision between them. Of course, like when it comes to GANs, anything you probably think about, there's probably at least like a dozen papers about. So there's also a lot of papers about GAN variants that try to learn bidirectional mappings both ways, but those never really took off. Oh, good question. What have we gained? So when we went to VAEs, we gained latent vectors, but we gave up density. And now with GANs, it seems like we gave up latent vectors that we can control. What you gained was much better samples. So when it comes to VAEs, like VAEs tend not to give you very good samples. VAEs are sort of characteristically always kind of blurry. They never really look good. VAEs on their own just never tend to give you very clean, crisp samples. But with GANs, as you saw with some of the examples, you can get very crisp, very clean, very good samples. But what you lost was like your sanity in trying to tune these systems. Yeah, at inference time, you throw away the discriminator and just use the generator. So at inference, you'll just draw a sample Z from the prior, pass through the generator, get your sample from your data. So it's very, very efficient at inference time. All right. So I mentioned that GANs used to be the go-to category of generative modeling for about 5 or 6 years. So what displaced them? And what displaced them was a very different category of models called diffusion models. Now, I need to put some caveats here. Diffusion model literature is crazy, right? Like you read these papers, they go through like 5 pages of math before they tell you at all what's going on. And there's like 3 different mathematical formalisms that lead to diffusion models that are all very different mathematically. And there's very different notation, very different terminology, very different mathematical formalisms between papers. So like this is a sub area that's crazy. So I need to put a big caveat here that I'm not gonna cover fully all the different variants of diffusion models with all of their proper mathematical formalism. Instead, what I'm going to try to do is give you an intuitive overview of diffusion models, as well as an intuitive geometric understanding of the most common form of diffusion models today, which are called rectified flow models. And you could teach many, many lectures about diffusion models and get into all the interesting mathematical nuance of all these flavors, but we just won't have time for that in 2/3 of one lecture, unfortunately. So with that caveat aside, the intuition behind diffusion models is actually kind of easy. So like with all generative models, we want to draw samples, and we kind of like GANs, we want to convert samples from a noise distribution Z into a data distribution PX. But the way that we're going to do that in diffusion models is totally different. GANs learn this deterministic mapping through the generator to map a Z directly to an X. With a diffusion model, we're going to do something more implicit, more indirect. So what we're going to do, first off, the first constraint in diffusion models is that the Z, the noise distribution, the noise always has to have the same shape as our data, right? So if you have an image that's like h by w by 3, then your noise distribution always has to be h by w by 3 as well. They have to be exactly the same shape. Now what we're going to do is consider very different versions of our data that are corrupted by increasing levels of noise. So here, if we have a data sample, which is this picture of a cat, then under the t equals 0, and then t is going to be our noise level, which ranges from 0 to 1. So at t equals 0, that means no noise. That means a totally clean data sample. T equals 0.3 is a little bit of noise. We add some of our noise we mix some of our noise Z into our data X. And if we go all the way to t equals 1, we get full noise. And those are going to be samples directly from our noise distribution. So somehow this t parameter is going to interpolate smoothly between our data distribution and our noise distribution. And this is the noise distribution, again, is going to be Gaussian, almost always Gaussian, something simple that we understand and can sample from. And now what we're going to do is train a neural network to do a little bit of incremental denoising. So the neural network is going to receive some sample, which is a piece of data, which has been corrupted with some intermediate amount of noise. And now the neural network is going to be trained to try to clean it up a little bit, remove just a little bit of the noise. So the training objective here is going to be neural network inputs, an image of with some amount of noise, and it tries to remove some of the noise. Then at inference time, what we're going to do is do an iterative procedure where we first draw a noise sample directly from our noise distribution PZ, and then iteratively apply the neural network to remove noise from that sample one at a time. So, the very first time we do this, we're going to draw a complete sample that's complete noise, and then the very first application of the network will be trying to remove noise from full noise. So it will basically be forced to hallucinate just a tiny whiff of data structure in that noise. And then, once we get to some slightly less noisy example, we're going to pass it back to the neural network and again ask it to remove just a little bit of noise from this now slightly denoised, slightly generated image. And then it'll get a little bit less noisy, and it'll get a little bit less noisy, and it'll get little bit less noisy. And eventually, if we set up all of this stuff correctly, then we want to get to a situation where we can draw a complete noise sample and then ask the network to remove noise from that complete sample Z of complete random noise until eventually we've removed all the noise and come up with a generated sample from the system. So that's kind of a weird setting. It's kind of a weird thing, but that's kind of the intuition behind diffusion models. Is the number of steps a fixed hyperparameter? It depends. So on this slide, I've intentionally I was sort of forced to be very vague about all these things. What is the noise? What does it mean to corrupt the data with respect to the noise? What does it mean to remove a little bit of the noise? What does it mean to apply it iteratively at inference? Because, like I said, there's so many different formalisms of diffusion. There's a lot of different variants about exactly what these mean in different situations. So this slide is intended to be a fairly high-level overview of diffusion, and then different specific implementations of diffusion models will have different concrete choices for what all these terms specifically mean. So, does this high-level picture of diffusion kind of make sense? Okay, so then let's make this more concrete. So now we're gonna jump from, general diffusion models to a particular category of diffusion models called rectified flow models. Some people may argue with me and say that rectified flow is not diffusion. Some people might say that they're different things. I don't really care. To me, rectified flow is a kind of diffusion model. Fight me. So with rectified flow, the intuition is basically this. We have this same thing. We have our P noise, we have our P data. And we're going to draw this geometrically because I think that's a nice way to gain intuition. Geometrically in 2 dimensions in particular because that's all that fits on the slide. But of course, these are going to be super, super high dimensional images, and Gaussians. Which is an easy way to get led astray, right? Because you know that intuitions that hold in 2 and 3 dimensions go totally out the window when you go to a lot of dimensions. It's really sad. It's sort of sad that we live in such a low dimensional universe because our intuitions that we build in this universe just don't really transfer to 100 dimensional spaces, 1,000 dimensional spaces. So always be aware, but it is what it is. We're stuck with the universe we got. So, the setup in rectified flow is that we've got, our distribution P noise, our distribution P data. P noise is something simple that we understand, we can sample from, we can compute integrals of, it's a very friendly distribution. P data, again, is something crazy, that's what the universe is using to give us images. Now, at every training iteration, we're going to sample a Z from our prior distribution and sample an X from our data distribution. We can draw a sample analytically because PZ is something simple that we control, and drawing a sample from the data distribution just means picking an example from your finite training set. Now, and you're also going to choose a T to be uniform on 0 to 1. Remember, T is our noise level, where T equals 0 means no noise, T equals 1 means all the noise. So now we're going to draw a line that points from our data sample X directly to our noise sample Z. And this line, this vector pointing from X to Z, we're going to call it V. This is going to be the velocity of a flow field. And then we set xt to be a point along this line, which is a linear interpolation between X and Z. So now we've got our noise sample Z, our data sample X, we've got the velocity vector between them, V, and we've picked a noisy, a noise version of our data, xt. And this is, in the previous slide when we said, get noisy data, this is what that means in the case of rectified flow models. It's a linear interpolation between a data sample and a noise sample. And now the training objective is very, very simple. So now we're going to train a neural network, f theta, so that's f with learnable parameters theta. That neural network is going to input the noisy sample xt, as well as the noise level t, and it's going to try to predict the green vector v. So that's it. That's all we need to do in rectified flow. The code for this is very simple. You would be shocked, how much obscurity there is when you read papers here, and it boils down to this very simple code. Drives me crazy that this is not made more clear in a lot of presentations of this. So then the training loop for rectified flow is extremely simple. You loop over your data set. At every iteration, you get Z, which is unit Gaussian of the same shape as X. You choose noise level T, which is uniform 0 to 1. You compute XT, which is a linear interpolation between X and Z. You give XT and T to your model. And then your loss is just the mean squared error between this ground truth V and the model prediction. And that's it. That's your training objective for rectified flow models. Contrast this with GANs. When you train rectified flow models, or really any kind of diffusion model, you have a loss that you can look at during training. When the loss goes down, the model is generally better. So like for those of us that went through half a decade of GAN madness, the first time you train a diffusion model and like there's a loss to look at, it's like, oh my God, this is an amazing thing. Like how many hours have we spent looking at GAN plots and they look like this? And you have no idea. It's like reading tea leaves to tell whether or not the model is working well. You train a diffusion model, you get this beautiful, smooth, exponential loss curve, and it just makes you so happy. So that's great. So then that's training for diffusion models. Now, what do we do at inference, right? Because, GANs are kind of easy at inference. GANs, you just have to take a Z, pass it through your generator, you get a data sample, very straightforward. But now with the diffusion model, or rectified flow model in this case, the model output itself is like kind of useless. Like, we get this XT, we get a V, like what are we going to do with this? Not super clear. So then at inference time, is where diffusion models get a little bit more complicated compared to GANs. So, at inference, we first will upfront choose a number of steps t, which is usually a fixed constant. And in the case of rectified flow models, t equals 50 is usually a good number to start with. Sometimes you can get down to t equals 30, and that works okay. Then what you're going to do is sample an x directly from your noise distribution. This is going to be pure noise that's sampled from your known noise distribution. Then you're going to evaluate then you're going to loop from t equals 1, you're going to march backwards to t equals 0. This is your noise level. And in this case, in this simple version, we're just sort of marching linearly from full noise 1 back to noise 0 perfectly clean. Then at the first iteration, we're going to take our xt that was at first full noise, pass it to the network along with the current noise level, and get the network's predicted VT. And remember what this VT is supposed to be in the case of rectified flow. This V, remember, was supposed to point from a data sample all the way to a noise sample. So then it's kind of geometrically obvious what you should do in the case of rectified flow. You should take a little step along that predicted V vector. Because the problem is this rectified flow model, it's not gonna, that V is not gonna point you all the way to a clean sample. It's just gonna get you started. It's gonna set you on a trajectory towards a clean sample. So we take a little step along that predicted V from the flow model to get a new X2, which is now a version of the data that has had a little bit of the noise removed from it by the model. And now we iterate this. So once we have this X 2/3, then we pass it back to the model and get another predicted V vector from the model. And remember, the V is supposed to point from clean data, from a clean sample, all the way to a noise sample. So then again, we can take a gradient step, take a little step along this predicted V to get another X 1/3. Repeat this thing again, evaluate the model again to get another predicted V, and then take a step in this case all the way to no noise, all the way to the end of that vector to get our predicted X0. And then that is our sample from our diffusion model. So, then the inference procedure you see here got a little bit more complicated compared to GANs. But what we gained here was sanity when you're training. You've regained that. And they tend to give you much better samples, and they tend to scale really well to large data sets and large models. And the code here is really simple, right? So we start off by taking a random sample, make it be perfectly random, then march backwards for t from 1 back to 0. At every noise level, you get a predicted V from the model, given your current sample as well as your t. Then you take what looks kind of like a gradient descent step on the model's predicted V and update the sample, and just repeat this whole thing in a loop. So then you can see, like, these diffusion models aren't so scary after all. You can actually fit a complete implementation of training and sampling from a rectified flow model in just a couple lines on one slide, which I think is very nice. Okay, so you might be asked, so this is pretty nice. I'm pretty happy that we're able to get to a full, right? This will actually work, right? Like if you take this code, you plug it in, like you plug in a reasonable model architecture, like this will actually work. Like this will actually convert to something kind of reasonable in a lot of cases. You're kind of hitting on the core problem in generative modeling that I've been thinking about a lot the last couple of days while reviewing these slides, right? The core problem in generative modeling is somehow you have a prior distribution, which is Z's, that you know how to sample from. You have a data distribution, which is X's, that you want to generate. And kind of the core problem in generative modeling is figuring out how to associate Z's and X's. And all your different categories to generative modeling kind of do it in different ways, right? In a VAE, you say, I'm going to have the model predict a Z and then predict an X and then try to force that Z to be something I know how to sample from, which doesn't super work that well. In a GAN, you're not supervising that relationship. Like the generator is kind of figuring out its own mapping from Z to X in a feed-forward way through this distributional matching objective that the discriminator is giving it. In diffusion, it's kind of figuring out by what ends up, it ends up having to integrate these curves. And there's a lot of different, actually like several different mathematical formalisms as to why objectives that look like this end up matching probability distributions in a reasonable way. But again, like the whole core problem is that we have no way ahead of time to pair up samples Z from our prior with samples X from our data. If we knew how to make that pairing and also knew how to sample from the prior, like you'd be done. And in some sense, all these different forms of generative modeling are different ways to square that circle and come up with a way to learn an association from Z to X, even though we don't, and be able to sample from Z, even though we don't have that association at training time. There's a lot of different interpretations of this that can get very, very heavy very quick, so I've tried to avoid them.